7.3 is going to venture beyond terminating decimals, which is what we've been working with in section 7.1 and 7.2, and we're going to look at non-terminating decimals. And in particular, these are called repeating decimals. There are other types of numbers that aren't repeating in decimal form, but those are irrational numbers, and that's outside of the content of this chapter, okay? So we're not talking about that. We're talking about the ones that repeat. So when was it that we said that a fraction could be written as a terminating decimal? What were the conditions to making that happen? Okay, say it louder for me, Cassidy. Okay, what has to be divisible by 2 and 5? Okay, so I'm going to expound a little bit upon your head, but the 2 and the 5 are really important. So the denominator of the simplified fraction, and it has to be the simplified fraction, okay? Has factors of 2 and or 5, doesn't have to be both, but 2 and or 5, and nothing else. I'll say no others since I'm running out of space. 2, 5, 2s and 5s, no 3s, no 7s, no 11s, stuff like that, right? None of that's going on. So what if the fraction cannot be written as a terminating decimal? Well, if the fraction is an integer over an integer, that makes it a rational number by definition, and does not terminate. Then it will repeat. So what we're going to be working in this section on, some of this section anyway, is taking our fractions and turning them into repeating decimals, and taking repeating decimals and turning them back into fractions. Okay? So the first one we see is one direction of that. We're going to find a decimal representation for 1 over 24. And because 24 has a 3 as a factor, it's 3 times 8. The 3 is what's going to make it not terminate. There's no way that the 3 can be reduced with anything in the numerator. So 1 over 24 is in simplified form. That 3 is causing a problem to making this a terminating decimal. So we actually find these just like we find terminating decimals. We do the division. I wrote that wrong. There we go. So we're dividing the number 1 by 24. And of course, 24 doesn't actually go into 1, so we use lots of decimal places to try and figure out what's happening. I'm just going to put 4 for now. I'm not sure if that's quite enough. I think it is, looking at my notes. But if you put too many or not enough, you can always add or take them away later, okay? So it's going to take 3 places before it's big enough to actually be divisible by 24, right? 10 doesn't work, 1 doesn't work, 24 will go in, though, to 100. How many times will 24 go into 100? 4. So the 4 needs to go above the whole number 100 as a 3-digit number, and then anything that came before that would be a 0, and the decimal point would come up as well. So it would look like this so far. What is 4 times 24? 96. So, whoops, I've got a 96 right here, and I would subtract. What's 100 minus 96? It's 4. And then, just like with terminating decimals, we bring down the next 0, and I've got the number 40. So how many times will 24 go into 40? Just once, right? So the 1 goes above that 0 that I just pulled down, and I would subtract off that 24, which would give me what? 16. And I'd bring down my next 0. How many times will 24 go into 160? It's 6. And you're welcome to use your calculator to do the in-between steps. The whole combined part that I'm doing right now right here, I expect to see this all written out. But you can use your calculator to find out what is 6 times 24. So what is 6 times 24? It is 144, which gives me a remainder of what? 16. Have we had that remainder show up before? Yeah, we have. Once you have a remainder show up again that you've already had before, and that's happening in these 2 steps right here, there's no more dividing that you have to do. Because no matter what I do, I'm going to keep getting 16. Because I'm going to get, 16, I pull down a 0, I'm going to get 144, and then I'm going to get a 16, and then it's going to cycle at that point, right? Now, I'll show you what happens when the remainder doesn't occur in the immediate step afterwards, because that's not always the case. But when it does occur immediately, like it did in this problem, what it means is that I'm going to keep getting this 6 over and over again. So when I put my repeating bar, it needs to be above only the 6, because it's only the 6 that's going to keep repeating after this point in time. So make sure that when you're putting your repeating bar, it's very clear what's repeating and that you don't end up putting it over like this. Don't make us guess. This would not be okay, because the 1 doesn't repeat, it's just the 6. So the representation of this in repeating decimal form is 0, 4, 1, 6 with the 6 only repeating. Now, this type of a number is in fact called a repeating decimal. And the repeating block of digits is called the repeat end. So on that last problem, the repeat end is just the number 6. And I said this out loud, but it's also written down just in case you forgot. I do expect to see the division when you convert these. I know your calculator can do it for you. I'm fully aware of that. And checking with your calculator is probably a really good idea. You should do that too. But I want to know that you know how to do all the division steps on your own. So for those of you who would be teaching this material to kids, this shows up in 5th grade. I know, we just got there with my kids, 5th grade, where they're doing this kind of division, all right? So 5th grade, 6th grade is going to be where this is going to be happening. And in general, they're not allowed to use calculators in 5th and 6th grade. I'm not going to guarantee you every school's like that, but I think that's a pretty general statement at this point. State tests in Oklahoma allow 7th graders to use calculators on their math tests, but they have to be calculators that do not have negative buttons. I don't know what's so special about negatives, but they can't have them. So, there you go. So nothing scientific or graphing or anything. All right, so we're going to do the same directions again on this problem. But the repeat end is going to look different, so I wanted you to have a comparison so that you can see it doesn't always end up just giving you the 16, 16, 16 like my last problem would have. So we're going to do the problem the same way. We have the 99 on the outside. We have our 29 on the inside. And of course, the 29 is smaller than the 99, so this will be a decimal point to give me the 29 with the 0. So how many times will 99 go into 290? It's twice. So above the entire expression of the 2, like what looks like 290 if you ignore the decimal place. So above the 0, the 2 will go. And there will be a decimal point right in line with the decimal point that's already there. And if you'd like to put zeros in front, you certainly can. So what is 2 times 99? 198. Yeah. And if you subtract, what do you get? What is it? 92. Thank you so much. 92. Okay, that's not the 198 I just had before, right? Like it's different. So I need to put a 0 here and pull a 0 down. Now I have 920. So how many times will 99 go into 920? It is 9. What's 9 times 920, or sorry, 9 times 99? 891. And if you subtract, what do you get? You get 29. Have you seen a 29 before? We actually started with it. Now this one occurs very quickly I mean, the repeating part occurs very quickly. So if you didn't happen to notice this and you tried to pull down another 0, hopefully at this point you'd be like, wait a minute. I've done 290 divided by 99, right? Like I already did that once before. So the question is, what's happening? Well, if I did accidentally try and subtract again, I would in fact get another 2 here. Like that's what would happen, right? If you recognize it earlier than that, you can see where it started to repeat. This actually repeated 2 steps later. Do you see that? 2 subtractions later is where my 29 showed up again. What that tells you is it tells you that the 2 and the 9 are repeating. And in particular, if you weren't sure, you could just do a couple more steps and you'd very quickly see this happen. Oh, look, there's a 2 again. Oh, look, it's followed by a 9, and I'll bet 2 comes next. Patterns, right? Yeah. So when you see that happening, either whether you notice it right away that the 29 repeated itself, or whether after a couple more iterations you realize, oh, it's the 29 that's repeating itself, what we do for writing down the answer is we write down the 29 and we make sure that the bar is above the 2 and the 9. And we don't write, like we would not do this. No, that's a no, right? You only want to write down as many as you really need in order to represent what's going on, and that would just be this 2 with the bar above the 2 and the 9. Okay. This is an interesting one. You may have actually known when you saw this one that this would be 2, 9 repeating. Did anybody look at that and go, I know that's going to be the answer? Sometimes people do when they divide by just 9s. For example, if you wrote down 4 over 9, you might automatically know that this is 0.4 repeating, and there's a reason for that. It's not just like, oh, what a cool trick. It's actually got a reason behind it, and we're going to explore a little bit of that reason this next example. So this next example has us go in the opposite direction. I am starting with a repeating decimal, and I need to turn it into a fraction. You might get the idea from what we just did with the 29 over 99 being 0.29 repeating, that this 0.61 repeating will be 61 over 99, and it will. But not all the problems work out quite so nicely. What if instead you had like this next problem, where there's a repeating part, but it's not the whole thing? This is not going to be 61 over 99. So I want to show you how to work with it in this case first, but recognizing that, yeah, this is going to be 61 over 99. That's fine, but that idea doesn't always work for all repeating sets of values, okay? So this is interesting. What I want you to first do is to write down n equals 0.61 repeating. You're just giving it a name. Boy, my handwriting got big all of a sudden. Let's make that a little smaller. Okay, so however many digits repeat. How many digits are repeating here? 2. There are 2 digits repeating. You're going to multiply both sides then by a power of 10 with that many zeros. So if I had 3 digits repeating, I'd be multiplying by 1,000. If I had 1 digit repeating, I'd only be multiplying by 10. Okay, so the number I multiply by is completely and totally determined by how many repeating values I have. 2 repeating values, I have a 1 followed by 2 zeros. And of course, with any equation, if you do it to the left side, you do it to the right side. Right and left, they go hand in hand. So the nice thing over here, of course, is this is just 100n. Okay, fine, great. But what happens when I multiply 0.61 repeating by 100? Well, what we really had, and this is sort of like my scratch work done here for a moment, is I have 61, 61, 61 a whole bunch of times, right? Like that's what's going on here. So if I multiply this number by 100, what happens? Right. So this decimal place ends up moving 2 decimals to the right. That's what happens when you multiply by tens. Decimal points move, right? Okay, so this will become, like you just said, 61.6161, and it keeps repeating. Is there a better way to write that? Well, yes. 61, because it's before the decimal point. You don't put any repeatings before the decimal points. That's never a thing. The decimal repeats at the 61 part afterwards. Okay, is everybody good with that? It kind of looks like I changed a 2-digit number into a 4-digit number, but I didn't. It's not what I did at all. All right, I just have stopped writing it at the earliest place I can stop writing this new value, which is 2 decimal places, or 2 places after the decimal point. So now I have 61.61 repeating. Now our goal at the end is to write this as n equals. Okay, so I started out with this piece right here. Right, n equals this decimal expression, and at the end I want it to say n equals a fraction expression. Does that make sense? Okay, I want to change it from a decimal to a fraction, so I start with it equaling a decimal, and at the end I want my decimal to be a fraction. But if I just divide this by 100, I haven't actually gotten anywhere because I still have decimals inside of a fraction, and that's not what I'm looking for. I need only whole numbers, right? Only integers. And right now I still have decimals involved. So there's one intermediate step that I need to do. What I've boxed in blue right now is a relationship. N is equal to 0.61 repeating. Agreed? Okay, so like with fractions, one of the things that we had as sort of an allowable operation is I can multiply by something as long as I multiply the top and the bottom by something. With equations, I can multiply by something as long as I multiply both sides of the equation by the same value. And it's true for addition and subtraction as well. If I add something to the left-hand side of an equation, I have to add something to the right-hand side of the equation, right? It's a balancing situation. So whatever I do to the left, I have to do to the right. So what I'm going to do is I'm actually going to subtract the n value from the left. But what does n equal? 0.61 repeating. So I'm going to subtract the 0.61 repeating from the right because they're equal. And as long as I've done something to the same thing to both sides, or if they've done equal things to both sides, that's an allowable operation because n and 0.61 repeating are equal to each other. So I want to subtract the n from the left because the left side has n's. And I want to subtract the decimal from the right because the right side has decimals. The beautiful thing that happens, of course, which was the whole goal, is that these become nothing, right? The 6-1 repeatings, they line up. And so they're all going to now go 6-1, 6-1, 6-1, 6-1, and it always cancels out. Yes, it repeats forever, but it repeats forever in both expressions, so it's always going to be 0 on that part of it. Which leaves me with a 61 on the right. And then what's 100n minus n? 99n. And so if I want to get n alone, what would I do as my last step? Yeah, divide by 99. So I end up getting a ratio of integers, 61 over 99. Which is what I told you was going to happen at the beginning. Okay, it's a weird process and you've probably not done that before. Has anybody seen that done before? Okay, we're going to do it again, but this time we're going to do it for the number that only has one digit repeating. So if I were to write this out, again, I'll use this sort of a scratch paper down here. This is 6 like this. Okay, everybody gets that, right? This is not the same value that I had before. It will not become 61 over 99, or else it would be the bar on top of the 6 and the 1, and it's not. So we start out the same way. We define this arbitrary thing, n, and it doesn't matter. If you don't like n, use another letter. It's fine. And it's 6-1 with just the 1 repeating, like this. It almost looks like a Z. Okay, so back over here I told you, we multiply both sides by a power of 10. So it's either going to be a 10 or a 100 or a 1,000 or a 10,000, whatever. But the number of zeros is determined by how many repeating parts I have. How many values repeat in this problem? 1, right? It's a two decimals, right? There's a 6 and a 1, but the 6 doesn't repeat, just the 1 does. So what will I multiply both sides by? 10. That's exactly right. I'm going to multiply both sides by 10, and of course I get 10n on the left. So let's figure out what's going to happen on the right, and I'll do it down here on this little scratch work so that we can think about it. So if I multiply this by 10, what's going to happen? Yeah, so the decimal is going to move 1 to the right, and you're going to get 6.1 repeating, and that's totally true. It's not a very helpful way of writing this. Because the original number I had showed the repeating part above the hundredths place, right? And this number that I've written shows the repeating part above the tenths place. Everybody good with that? I mean, you see what I'm saying? And I really, really need these repeating parts to line up so that they subtract off. Like, that's my real goal. I need the repeating bars to be lining up above the same place value, and right now they're not. But it's actually true, although it's not how we would normally write it, that I could write this, whoops, like this, right? It's not a simplified, very nice looking way of writing it as a final answer, but it's true. If I put the repeating bar above the hundredths place, it's going to be equal to the same thing as if I put it above the tenths place, because I've written in the additional 1 in that location. So this is the one that's most helpful because it's the one that's going to match up later. So over here, I'm going to write down the 6.1 with the 1 repeating above the hundredths place. But I need the repeating part to go away before I do any division. So I use the original piece of information to do a subtraction. I subtract from n on the left, I subtract n on the left, and I subtract 0.61 repeating on the right. And the reason I do that is because the 1 repeatings line up, and I need them to line up. If they don't line up, I can't continue. I can't simplify things. So this cancels. 10n minus n is 9n. And on the right, what's 6.1 minus 0.6? 5.5. Perfect. Okay, everybody good so far? 5.5. I realize there's a decimal, in case you're concerned that I didn't see that. I do. I see it. We will fix it. But we've made progress because there's no more repeating parts. I know we still have decimals, but there's no more repeatings. So I do, in fact, want to divide by 9, right? But this cannot be my final answer because I'm supposed to be getting an integer over an integer. That's what the directions said, right? A and B are integers. So I'm not done. Yeah, who said that? Elizabeth? Yeah, say it louder. Okay, and I think you mean by 10 over 10, is that right? Yes, that's exactly what I want to do. That is allowable, right? I can do the same thing to the top and the bottom of a fraction. And by multiplying by 10 on the top, what will that 5.5 become? An integer, yeah, the integer 55 specifically. And I have 90 on bottom. So we definitely have integer over integer. That's good news. Yay for us. It's not in reduced form, though, and we're always going to put things in reduced form when there's a way to do that. So what do 55 and 90 both have in common? A 5. So what is 55 divided by 5? 11. And what is 90 divided by 5? 18. Yes, ma'am. So this one is the right answer. And if you want to confirm it, right, there's not a real good way for you to actually work this problem in your calculator and get to the answer, but there's an easy way for your calculator to verify that you got to the right answer. If you take 11 over 18 and do your calculator, just put 11 divided by 18. Do you get 0.61 with the 1 repeating? You do. So you can verify that you got the right answer at that point as well. Okay? I think I have just enough time to show you something super cool that you maybe didn't know before we end today. We're just going to take the decimal 0.9 repeating and do the same thing. Okay, so I'm going to move pretty quickly because we've done a couple of them now, and I'm running out of time. But we've got n equal to 0.9 repeating. How many repeating values do I have? 1. So what do I multiply by on both sides? 10. Perfect. Okay, so I've got 10n on the left. And then this 0.9 times 10 would end up giving me 9.9 repeating. Right? Because 0.9 repeating means point and then lots of 9s. So we move the decimal 1 over. It's like the last problem we did. And we go back to subtracting exactly what we started with. N from the left and 0.9 repeating from the right. So what is 10n minus n? 9n. And what is 9.9 repeating minus 0.9 repeating? It's 9. And if I divide by 9, what in the world happened? What? Oh yeah, for real. Hence, 0.9 repeating equals 1. It's not wrong. It's actually true. I actually remember the first time that somebody argued this. They didn't show me this method for doing it, but I was in high school. And I think it was my 9th grade geometry teacher, if I'm remembering the right classroom, because I remember classrooms. And we had lots of argument about the fact that there's no way that could be true from very smart people in the class. But it is absolutely 100% true, and I actually just proved it to you.